Welcome back to LectureCast-Prolog. In the last module we learned what recursion is, a base case that stops, and a recursive case that shrinks the problem and calls itself. Today we put that idea to work. We will apply the very same pattern to the two data structures you will use constantly in Prolog, compound terms, which package data together, and lists, which are really just compound terms in disguise. By the end you will see one recursive shape repeated everywhere, from a family tree to a binary tree. First, a quick callback. In Module 4 we built recursion from 3 iron rules: always write the base case, make every recursive call shrink toward it, and then trust the recursion to handle the rest. We traced factorial all the way down to 0, and watched the answers multiply on the way back up. None of that changes today. What changes is the data. Instead of counting down numbers, we will walk down lists and dig into nested structures, but the skeleton, base case plus recursive step, stays exactly the same. Let us start with structure. A compound term is a functor, a name written in lowercase, followed by one or more arguments in parentheses. Date of 2024, 10/21. Point of 3, 4. Person of Tom and age 25. The arguments can be anything: atoms, variables, even other compound terms. Two things matter here: the functor name, and the arity, which is simply how many arguments it has. Together they form the term's identity. Point with 2 arguments and point with 3 arguments are completely different predicates. Prolog never confuses them. Because an argument can itself be a compound term, structures nest as deeply as you like. Here an address holds a street, a city, and a province, and each of those is its own little term. Now watch how we read the data back out. We do not write getters or accessors. We just describe the shape we want, and let unification fill in the blanks. Address, underscore, city of X, underscore. The underscore says I do not care about this part, the variable X catches the city. One pattern, and Prolog hands you Ningbo. This is the same unification engine from Module 3, now reaching inside nested data. Here is the idea that ties this whole module together. A list is not a new kind of thing. It is just a compound term in disguise. The list A, B, C is really a chain: A, joined to the list B, C, joined to the list C, joined to the empty list. Peel it apart one layer at a time and you get a head joined to a tail, until you hit the empty list at the very end. That empty list is the end marker of the chain. And that is exactly why, in list recursion, the base case is almost always the empty list. It is where the chain stops. The single most important operation on a list is splitting it into head and tail. Write square bracket, H, bar, T. The head is the first element, the tail is the list of everything else. Unify that against A, B, C, D, and H becomes A while T becomes the list B, C, D. You can peel off more than one at a time: X, Y, bar rest grabs the first 2 and leaves the remainder. And for a one-element list, the head is that element and the tail is the empty list. Every list recursion is built on this one move: take the head, recurse on the tail. Let me show you the pattern in motion. Watch what happens as we recurse down a list. Each step pulls off the head and hands the shorter tail to the next call. The list gets smaller: B, C, D, then C, D, then D, then the empty list. The moment we reach the empty list, the base case fires, and there is nothing left to recurse on. This is the heartbeat of list programming: process the head, then recurse on the tail, and because the tail is always shorter, you are guaranteed to reach the empty list and stop. Keep this shrinking picture in your head for every example that follows. Now let us name that pattern. The universal template has 2 clauses, one for the empty list, the base case, and one for head bar tail, where you process the head and then recurse on the tail. Almost every list predicate is a variation on this. In the checking variant, like member, you ask a yes or no question as you walk down. In the computing variant, like length or sum, you combine the head with the result coming back from the tail. In the building variant, like copy, you rebuild a new list as you go. Same skeleton, 3 jobs. Learn the skeleton once, and you can write all 3. Append is the example that makes the pattern click. It joins 2 lists. The base case says, appending the empty list to L just gives you L. The recursive case peels the head off the first list, appends the rest, and then puts that head back on the front of the result. Here is the beautiful part, and it should feel familiar. Just like factorial in Module 4, where the multiplications happened on the way back up the stack, append builds its answer on the way back. Going down, it strips heads off and remembers them. Coming back, it stitches them onto the front of the growing result, one at a time, until the full joined list emerges. Put member and append side by side, and you meet Prolog's superpower. The same definition runs in every direction. Member can check whether an element is present, or generate every element one at a time, or even build a list that contains a given item. Append is even more striking. Run it forward to concatenate 2 lists. Run it backward to split a list into every possible front and back. Give it a known prefix, and it strips that prefix off. Or use it to test whether something is a sublist. You wrote one rule about what joining means. Prolog gives you concatenation, splitting, and searching, all for free. Reversing a list shows why how you recurse matters. The naive version is honest but slow, reverse the tail, then append the head onto the very end. Appending to the end walks the whole list every time, so reversing costs n² steps. The accumulator version is linear. Picture a stack of cards. You take each card off the top of the input and drop it onto a new pile. Because the last card you pick lands on top, the new pile comes out reversed, naturally, in a single pass. The trick is carrying a second argument, the accumulator, that holds the answer as it grows. That accumulator idea has a name, tail recursion. Compare it with factorial from Module 4. There, every call had unfinished work waiting, the multiply on the way back, so the machine had to remember the whole way down before it could come back up. A tail recursive predicate finishes its work before the recursive call, carrying the running result along in the accumulator. There is nothing to come back for. The advantages are real, no waiting for returns, no growing stack, and no stack overflow on a list of 1,000,000 elements. When you need recursion that stays safe on big data, reach for an accumulator. Let us finish by combining everything. A binary tree is just a compound term, tree of a root, a left subtree, and a right subtree, with the atom nil for an empty tree. To check whether an element is in the tree, we use the same base plus recursive shape, but now the recursive step branches 2 ways. The element is found if it is the root, otherwise, look in the left subtree, or look in the right subtree. That is double recursion, the same idea we keep reusing. Notice the through line of the whole module, one recursive pattern, applied to a list, then to a nested structure, then to a branching tree. So, to recap. Compound terms package data, and a functor name plus its arity is the term's identity. Lists are compound terms in disguise, which is why the base case is always the empty list. The list recursion template, process the head and recurse on the tail, powers member, append, length, and the rest. Accumulators give you tail recursion, and safety on big lists. And one base plus recursive shape stretches all the way from lists to trees. Next time, in Module 6, we will see why order matters, how the arrangement of your clauses and goals can send Prolog into an infinite loop, and how to avoid the traps. See you there.